All right, here we go, please. This won't surprise anybody, but we got more math. More math. Well, no, you signed up for AP chemistry, which is math. All right. Tomorrow we're going to do a lab. Tomorrow. Okay, I'm getting annoyed. I'm getting pretty close. Getting pretty ornery. Tomorrow we're going to do a calorimetry lab. So make sure you're paying attention to this, my friends. Here we go. Calorimetry. We briefly talked about it yesterday, correct? All right. So we have a reaction that takes place in water. We measure how much the temperature goes up. We use some fancy math skills and we know what its change in enthalpy is. All right, then we got here, I believe yesterday, you don't really have to know a ton about this, but specific heat and heat capacity. So the amount of energy required to raise the temperature of substance by 1 Kelvin is its heat capacity. We define specific heat capacity, or simply specific heat, as the amount of energy required to raise the temperature 1 gram of a substance by 1 K. So you don't really have to know that. They're very similar. Like, they're not the exact, but they're pretty much the same thing. So what we absolutely need to know is this. And you're going to actually write this in a whole different way, but just kind of go with me. So specific heat then is heat transfer divided by mass times temperature, or S equals Q over M delta times delta T. Now, hold on. I'll come back to that, I think. Wait. I will. I just said I'll come back to that, I think. Okay. So if you want to write that down, you can. We're going to see it in 3 more slides in the way that we use it more often. All right. Now, like I said a second ago, we'll see it in a different place. This mass, that's going to end up being the mass of our total solution. So it's tricky there. When we mix this solution and measure these things, it will be the total mass, just not the mass of the solute. That's probably where most kids mess up most of the time. All right, I'm going to go forward. You'll see it again, I promise. All right, so what we will do tomorrow is called constant pressure calorimetry, oh, that's funny, also known as coffee cup calorimetry, or in Utah, hot chocolate cup calorimetry. So what we'll do is we'll just take some styrofoam cups. We put a couple of them. We put a little top on. I don't put a cork. I just put a cup that I've cut off. So it's insulated. So that there's not a lot of heat loss to anything except for the water. And then we put a piece of glass in here to mix things around. Ours will be a piece of metal. And we have our reaction take place in here. As that reaction proceeds, it will either give off or take in energy. Go ahead. There's just a tiny bit of work. If it's a gas, if I put carbon dioxide and vinegar in, there's a lot of work done. But if I'm just making Ag plus and Cl minus become AgCl solid, there isn't a ton of work done. It's mostly 99% heat if it's at constant pressure. Go ahead.
We're making hot chocolate?
No, we're not. We're just using cups, styrofoam cups. Go ahead.
Would the glass stir add or no, that wouldn't add work.
It won't add work. The glass stir, it's part of the system, so some energy will be lost there, so that adds error, but it's not that much. No. All right. So by carrying out a reaction in an aqueous solution in a simple calorimeter such as this, one can indirectly measure the heat change for the system by measuring the heat change for the water. Okay. Whatever the heat change is from the water, the system's the opposite. So if the water gained 50, then the system had to lose 50. We okay with that? Okay. So because specific heat for water is well known, this is a number we need to have memorized, 4.184 joules per mole Kelvin. We can measure delta H for this reaction with this equation. Q equals ms delta T. I'll come back.
Hey, Jake.
Yeah.
So, specific heat, is that like, more like water, like, is that as hot as it will get, or is that like?
Specific heat is just the energy required to raise it 1 degree.
Okay.
So for water, it's 4.184. For aluminum, it'd be like 1.9 or something like that. Go ahead.
So what is 1 joule?
It's just a unit of energy. It's a kilogram meter per second per second. Like, what is that? That's its unit. It's the ability to do work, but since work and heat are related, you can have the same unit, but they are sort of weird. It's just it's a unit of energy. Okay. Now, in order to get our endo and exothermic things to work, we add a negative sign. So Q equals negative SM delta T. Now, we don't always have to do that, but you should. So I'll come back to that in a second. This is true. This will tell me the heat, but if I want to know if it was lost or gained, we're going to throw that negative on to start so that it goes with our convention that a negative number means it's exothermic and a positive number means it's endothermic. You okay with that? Bless you. So I would memorize this as Q is equal to, and I always write it this way, it doesn't matter, but I like my negative sign in the middle. This way, my Q is negative, I know it's exothermic. My Q is positive, it's endothermic. Yes?
So what does the thermometer tell us?
The change in temperature. That's the thermometer is this delta T, change in temp. So it will be in here, we'll say before I add anything, whoops, it's at room temperature, 25 degrees Celsius. Then I add my NaOH and it dissolves. And this goes up to 42. So then my delta T, it would have gained 17. Okay with that?
Yeah.
All right. Now I would know that's exothermic, right?
Yeah.
Because it went up. If I don't have that negative, it's a positive value. And you might think it's endothermic. Well, this, without the negative, it's just telling you the energy. Doesn't care positive or negative, but we really do care about positive or negative. So that negative makes it work with our convention. It's a negative is exo, positive is endo. Okay, so you will get some problems that are somewhat complicated. So I have these steps. You can either take a picture of them or write super fast. These are useful. Why are there arrows? To help you follow along. These problems, they can be tricky, but they're a lot like what we've done before. If you just follow the steps in the right way, you can get them. You can definitely work through them and they're not that bad. Where'd it go? Probably on that screen already. Okay, these are on the right side screen. I'll leave them up there if you want to keep writing them down. Okay, so a typical calorimetry question on an AP test, and they are really common, by the way, would be like what we're about to do. Let me get rid of this stupid message. You probably wonder why I don't just hit update now, but I don't because it doesn't work. Every time I do it, it takes like 6 minutes, and then it says at the end, update failed. It's just a sucker button. Okay. So typically what they'll do, you'll have a problem, and we'll do some in a minute, where you throw the mass of your solute in or whatever's going to react, if it's a reaction. So you keep track of that mass, so you know how many grams, you're going to convert those to moles eventually. So you're going to throw them in, you're going to measure how much the temperature goes, and we're going to use math to figure out what the heat is. Then we're going to use that value for how many grams we had to figure out what it is per mole. And then we can use it in any picket fence we feel like. Sound good? Okay, so here is your typical problem. If you have 30 grams of sulfuric acid and you add it to 250 milliliters of water, the temperature rises from 23K to 31K. What is the heat gained or lost in this process? What's our variable for heat in this chapter? Don't do it to me. Q. So we just wrote an equation. What is the heat gain? Well, Q, I just learned, is equal to negative SM delta T, correct? All right, negative SM delta T. So I'm just going to plug these things in. So S is a variable or a constant. It is for water, negative 4.184 joules. The value, yes, 4.184. All right, now M.
Oh, that's just because it's 1 calorie, right?
Per joule. M is the mass of the solution. So, does this give you the mass of the solution? All right, for water, milliliters and grams are the same. So we just have to add the two of them together. 30 plus 250. So I have 280. Then my change in temperature.
Wait a minute. 280 grams?
Yeah, 250 of water, 30 grams. Oh, you're not. Milliliters is grams. That's 250. But then we added 30 more grams of this stuff. Fair enough?
Yeah, that makes sense.
Okay. And then we need delta T. We take our final minus our initial. So 31 minus 23 is?
Are the units going to be a problem?
No, because this is joule per mole, Kelvin, whatever. Like, and we can convert that to moles if we wanted to. Like, or it's per gram, I think. Anyway, no, they're not, is the short answer. Okay, there is a trick here, though. What is this math-wise? What did this turn out to be? 93 what?
72.2.
We'll just call that good enough for right now. Okay, now we need to be careful here. if you write negative 9372, they're going to mark it wrong, which is annoying. And I know it's annoying. And you're going to say, you just lied to me. Well, get used to it. This is the problem. What does this question ask you? All right. So you would not put a negative. Just go with me here. You would say in word form, I don't want to erase. You would say 9372 joules were lost. They're looking for you, and you know what? They know that a negative means it was lost, but they're looking for you to prove to them that you know a negative meant it was lost. But, this is where you're like, why are you such a jerk, Davidson? Remember a minute ago, I said that Q was equal to SM delta T, but we throw in a negative so it works. Part A is just asking for this. All right, we put the negative so it makes sense to us that this is exothermic. So make sure and answer the question the correct way. What is the heat gained or lost? 9372 joules were lost. Okay, yes.
So how does that even work? Because you're gaining heat, like the temperature.
The water gained heat, but the sulfuric acid, like dissolving, it's the one that gave off that energy as its bonds were broken. All right, now we're on part B. So we did this. We used Q equals negative SM delta T to solve for the joules. Remember to make sure M is the mass of the entire solution. So that's where the 280 came from. Convert to kilojoules, you're going to use that eventually. So you can answer it like that. That's not a problem. Just make sure right here, we want kilojoules per mole, but that answer was in joules because 4.184 is in joules. Okay, so it says find the moles of the solute given by dividing the given mass by the molar mass of the solute. All right, so this would be the answer if this was the same as the molar mass of that. But it isn't. So stick with me. It wants it in kilojoules per mole. So I'm going to convert this to and those are kilojoules. But did it give me an entire mole? No. It gave me exactly 30 grams, and the molar mass of H2SO4 is 98 grams per 1 mole. 0.306 is the answer, if I remember from last year.
I can't remember that long ago.
What's that? I mean, I did it in my head real fast. It's over. When I opened this up, I just went and deleted all the answers, so I just remember it from watching it earlier. Yep. There you go. That's true. Okay, so I have 0.306 moles that you had. I have the kilojoules. I'm just going to divide them, because that gives me kilojoules per mole, right? So if I take that and divide it by 0.306, why is it shaking so much today? Negative what? 30.63 kilojoules, and that's per 1 mole. Okay, so what this number means, it goes back to what we were talking about yesterday. If I were to write, I'll come back here, by the way, don't stress, but if I were to write the dissolution of sulfuric acid to be H2SO4 goes to 2H plus SO4 minus 2. It's just dissolving, or dissociating is the better word. Are you okay with that? And then I could say delta H equals negative 30 point whatever it was. The math we just did is the thing that would be written for the equation. Who's with me? 1, 2, 3, 4, 5. Okay, well, let's move on anyway. We're going to do more, but that's what we just solved for. The kilojoules per mole is this delta H. Yes, Fabian.
And this is because it's giving out energy because the molecules are breaking. Breaking means energy, joining means using energy, right?
Yeah, like sometimes it requires energy to break though, not break. These are not really breaking in a typical bond formation and breaking. These are dissociating. So breaking, that statement's true. Dissociating, it's not always true. Okay, now,
Because sometimes things don't naturally dissociate. Or spontaneous.
yeah. Okay, part C. Let me erase this. Part C. How many grams of sulfuric acid would you need to raise the temperature of 425 grams of solution, 20 Kelvin? All right, so we look over here at that list. All right, we are going to, we already did this, by the way. We found our kilojoules, then divided by moles. We're here. Use the given info to solve for the heat needed. That's Q. The given info, I have everything I need to solve for Q right here. Now, Q isn't grams, but I need to find it before I can find grams. All right, so I know that Q, okay, I don't know, could have sworn I, is equal to negative SM delta T. So I'm going to plug that in. Q is equal to negative 4.184. The mass, it tells you, is 425. And the delta T, it says raise the temperature 20 Kelvin. So that's a positive value. Somebody type that in for me. Yes,
Negative 4.184, that's joules, right?
that's joules.
So what is S stand for?
S stands for the specific heat for water. It's way back here.
I have it in my notes.
All right, it's like right at the very start. It's how much joules there is in 1 calorie, or it's the energy required to raise it 1 degree Celsius. Okay, did anyone type this in? Isn't it like 36,000 or 35? Negative, thank you.
Yeah, negative. That was in there.
Okay. Hi guys. It doesn't matter. Is it 6.4? Okay. All right, now, is that my answer? No, that's Q. Whoops. I don't know what I'm putting here. Okay, now, use a picket fence that starts with the heat needed and solves for grams of solute. Use your kilojoules per mole and your molar mass to complete the picket fence. Okay, so here we go. I've got a picket fence. I need to have things in kilojoules. So this better really be what? I'm just going to say that because it's good enough. All right, so that's what I'm going to start with.
Why would you start with that instead of the 20?
Instead of the what?
The 20?
Right here?
Yeah.
I don't use Kelvin in my picket fence.
Oh,
I have a relationship between kilojoules and grams. Sort of. It's this. Remember delta H for this? Now, it's really per mole, but as a chapter 5 AP chemistry student, I should be familiar with grams and moles and that they talk to each other. Okay, so here we go. And I know I can see the glossiness of your eyes. I know you're like, what is going on? But we can do it. I know what must be down here, what unit? It's got to be kilojoules. And I know that I found an answer right here, and it was?
It was 30.63.
Yep, and that was per 1 mole. All right, then, and this was the H2SO4, in case you cared. So what must be down here?
The mole is 425 grams.
No, the mole of sulfuric acid. And I already use this. I don't use that. I use its mass from the periodic table. 98 grams of H2SO4, which is dandy because what am I asking you to solve for?
That.
Whoops, that's supposed to be a circle, not a half cross out. So my kilojoules disappear, my moles disappear, and I'm left with grams of H2SO4 on top. That is what I want. So there's a 90% chance I set this up correctly. It's higher than that, it's 99.
Where do you get the 30.63?
That was an answer from earlier. Whoa, what did I just do?
Yeah, it was the one,
It was right here, it's kind of hidden. It's where, so we used our math to find how much heat. The next thing we did was to relate it per mole so that then I could use it in a picket fence. What did we end up with?
113.77. Or 78.
That's good enough. Okay, so ultimately, what I was able to do, I was able to use my coffee cup calorimeter to see how much heat was changed per the mass I put in. I was able to convert that to moles or per mole. Then I was able to make a prediction. I could now do this for anything I want. I could choose any temperature I want and find out how many grams it would require to do that. Okay, has anyone ever had a MRE, a military meal?
Yeah.
All right, and
Oh, is that what the little packet thing is?
okay, the packet things, it's not this exact chemical, but it's the same math. Some engineer out there somewhere said, all right, we need to heat this beef macaroni. That was my favorite one. All right, it has this mass. There's this little metal thing that you drop in and add water, and a reaction happens that gives off heat. A known amount of heat, that heat should transfer to the macaroni and make it warm. So yeah, it's this exact thing. It is cool. Okay,
Oh, is that how hand warmers work?
hand warmers are similar. Yeah, it's not a solution, but it's the same thing. Yep. You're taking iron, solid, reacting it with oxygen gas to make Fe2O3, and that has some sort of delta H that's a negative, so we get the heat out of that. It's just rust forming in there.
Wait, so rust?
You open them. Once you open them, they're now exposed to the oxygen, and you like move them around, and then the reaction will start.
Yeah, that's why they tell you if it gets cold to rub them again. So that
Yep.
they get more oxygen.
Yep, and you're good. Say that again.
Is it just like really powdered so oxidized?
Right, it's really refined iron, so it happens a lot more efficiently. Because most iron that we find just around, it's already oxidized. Like it's not going to. So they'll refine it nice. They'll put it in there, and there's some other things there to hold the heat as well, so it lasts longer and it doesn't just burn you. I don't know what it is. It's probably just sand. There's other things in there. Anyway, and it's all sealed with no oxygen. Once we tear the seal, then it happens. Now, there are other hand warmers that you can boil and reuse. Anyone seen those? And those are solutions. So we boil them to put them into solution, and then we take it skiing and we get cold and you snap that tiny little metal thing, and the solution starts to turn solid, and you get the heat back out that you put in. But there's definitely calorimetry in these, because I mean, this is a litigious world. If you made this too hot and everyone burned their hands, you wouldn't be in business very long.
Wait a minute, you could make them even hotter?
Absolutely. Hold on. Enthalpy is an extensive property. It depends on how much. So that little bag of iron, all we would have to do is change the ratios to sand and iron. It's probably not just sand off a beach, but it's probably silicon dioxide. But go ahead.
Can that be one of our labs? We make homemade hand warmers.
I don't know. Tomorrow we're making heat, but you can't touch that. That stuff will burn the crap out of you. Okay, try this problem right here if you would. Try that problem. Oh, delta is impossible to type in this program, so there's a little delta that's missing right here.
So isn't it the same?
It's the same process as all that over there. Okay, I'm going to pause it. Grace isn't here to get a U if I don't unpause it. I just ran into that and it hurt the person I trust.
David, then you don't trust anyone in this room.
Yeah, I do. Okay, how come I didn't put a negative sign here? I don't need to. Could I? Sure.
Oh, that's a good way to go. Make it positive.
Yeah, this is if you're finding just heat gained or lost, you don't need the negative. You need the negative. You need to know eventually. Anyway, moving on. 4.184. The mass is, it's water up here and 50 grams here. So 350, right? And I know you're like, well, why wasn't it down here? This one gave you the volume and a density. So that's why we had to do it a little bit different. And then the delta T, it rises again. So it's a positive 10. And you got what number?
14,644.
Okay, those would be joules. The next thing I would do is convert them to kilojoules.
So 14.64.
Who was at least able to do that? And I would say lost, by the way. Okay, so there was that many kilojoules lost by the system. If this was the AP test, by the way, it would be very specific. It would say, what is the heat gained or lost by the system? Because some smart kid would say, well, which one? And then I'd say, I hate you people. Okay, now, B, kilojoules per mole. I have kilojoules. It's 14.64 kilojoules. I need it per mole. So I'm going to figure out 50 grams divided by 56, 54.
56.
And so you have a 0.9 something?
0.892.
Okay, 8928 moles. And the answer is?
16.42.
Okay, and it should be a negative. Good. How did you know it was a negative?
Because 14 was a negative.
All right, because it's lost.
You're gonna need.
I know.
Well, it doesn't matter
It's-
if you change it
it's
out of
oh well.
negative because
Does
it'll
it matter
be-
that much though?
It does matter here, but once again down here, no. Because then you're going to get a negative mass, and all of you are like, you can't have a negative mass, and that's true. So anyway, now down here. Oh, so annoying. I'm going to have to erase for a while here. Okay, so part C, what was the first step? Do you remember?
Find Q.
Find Q. Come on, the picket fence is second. Okay, to save time, what the, oh, all right, Q. Oh my goodness.
Go click the pen.
Yeah. Don't hit the button.
Okay, we're screwed. We solved for Q by plugging crap in. To save time, what was Q?
It was -813.
Do we agree with that? All right.
And then when you convert it.
You start that with your picket fence and you're solving for grams. So right here is your answer to Q. Pretend I wrote it in white just for fun. The next step is your mole per kilojoule from here. right? Mole on top, kilojoule on bottom. The next stop, mole had to come down. Sorry though, JC, on this video. Sorry, the pen just stopped working. And then, so that's mole, and then this would be the molar mass of KOH again. And we got what? 277.
I got 278.
Same thing, good enough. Yes, Reese.
Never mind.
Okay, I forgot to. Let me turn this off and on again. That's computer 101, right?
It wouldn't matter if you have negative stuff, because won't they cancel each other out eventually?
Yeah, because I guess you're
In that
given,
one it did.
yeah, you'd have a negative up here and then the kilojoules per mole was a negative. Yeah, so they do cancel out actually, you're right. Okay, I don't know. See if this works.
I'm excited to learn more about them.
Why would it? Why would it work?
Davidson, how much does purified iron dust cost?
I don't know. Look it up.
Probably a lot.